Okay. So today we're going to be talking about fossil fuel technologies, and we're mainly going to be thinking about things in the sort of energy, electricity, power sector. And over the next couple sessions, we'll talk about non-fossil fuel technologies and then transportation technologies. Okay, so today, is actually everyone seeing the screen? I have this on my iPad and it's not showing anything for some reason.
Yeah, I can see it.
Yeah, we can see the screen with the dinosaur.
Okay, I have a confirmation here. All right. Okay, so fossil fuels, these are fuels that are formed by decomposition of dead organisms. So they're actually literally coming from fossils. So the benefits of this sort of materials that it contains sort of high percentages of carbon, which are sort of ideal for combustion. And that's going to allow us to extract energy and useful work from. So you've got three common sort of fossil fuels, and those are basically in your forms of liquid, gaseous, and solid, right? So petroleum is the common liquid. So this is analogous to crude oil and petroleum products. You've got natural gas, which is your gaseous form, and then coal, which is the solid form of fossil fuels. And there are several different, I would say, qualities of coal: lignite, bituminous, and anthracite, and that's sort of in the order of quality. And we'll talk about what these grades sort of refer to in a little bit. Okay, so thinking specifically about the use of fossil fuels for electricity generation. So today we're mainly going to focus on the solid and gaseous forms. There definitely is some use of oil in electricity production, but that's going to be really sort of dwarfed by coal and natural gas. And where petroleum really comes into play is once we'll start to be talking about the transportation technologies in a couple lectures. Okay, so coal versus natural gas chemistry. So this chemical compound on the left that you see is like one sort of example type of structure that you might find in coal. And so it is just these massive carbon chains and rings. And one of the things that you'll note is that you often have other impurities, we'll call them, within the molecular compound. So you have things like sulfur, or you have things like nitrogen, and that has important implications for byproducts of combustion of this. On the right-hand side, we have methane, which is what natural gas is. So CH4, as you can see, it's substantially simpler in terms of its molecular form compared to coal. But this also includes impurities, right? You don't get these like streams of just pure natural gas. Other things that you extract alongside natural gas include things like carbon dioxide, hydrogen sulfide, water vapor, and so on and so forth. So these are the sort of basic chemical displays for these fuels. And note that while natural gas is going to consistently always be this CH4 molecule, the example on the left is not, not all coal kind of looks like this. It'll be it'll be in similar sorts of forms, but not exactly like this molecule. Okay, so thinking about coal and natural gas in terms of energy content. So we had talked about this a little bit in last class, but this gives you hopefully some perspective about some of the energy density. And so as I was mentioning, lignite has sort of the lowest quality of coal, which means the energy density is quite low. And we much prefer to have things like bituminous and anthracite due to the higher energy density of the coal. And actually, in the U.S., this country actually has is known for having sort of higher quality reserves of coal, and so there's a lot of bituminous and anthracite mainly being produced out of the U.S. In terms of natural gas, we talked about the energy density being about 1,000 BTUs per cubic feet. This is equivalent to about 30 to 40 megajoules per cubic meter. There's some range of this, again, depending on the density of the gas, as well as impurities. So total reserves. So the reserve refers to the total amount of supply of that fuel sort of worldwide. I mean, you can have reserves for specific countries, but generally we consider this worldwide. And these numbers can actually change, right? As better extraction technologies come into play, what we consider to be sort of feasibly extractable, that number changes over time. And that's an important consideration for which we'll talk about that happened at this point, like a decade and a half ago, for natural gas in particular. And worldwide annual primary energy consumption looks something like this. So I'm going to give a sort of visual of some of these reserves. Okay, so global energy demand and resources. So this little blue box up here refers to the total amount of energy consumed by humans. And then you can see kind of the size of our energy resources. And note that this blue box on top it comprises of a whole bunch of different fuels, right? It's not just, it's not being satisfied just by one particular fuel. So we can see here sort of the quantity in terms of energy resources. Sort of on the bottom, we have renewable resources, but this is, this larger box is not something that you'd be able to sort of feasibly take advantage of the whole thing, right? This would essentially mean you'd have to, this is what you would get if you covered literally the entire globe, right, in solar panels. But it does speak to kind of availability of resources in terms of sort of what's raw and available. All right. Okay, so how does coal get mined? So basics of coal mining. There's basically a whole bunch of different ways that we extract coal resources, and this diagram shows kind of a comprehensive set of the different techniques that are used. You can see that some of these are going to be sort of a lot more destructive than others, where you're kind of demolishing entire mountainsides, versus sort of digging down into these sort of deeper mines, and a lot of the way techniques that are employed depend a lot on where and how accessible the coal resources are. There's definitely substantial sort of environmental damages. So this is one example that you can see using a technique called strip mining. And so, you know, we often think about, especially in the energy domain, thinking about damages associated with coal use from combustion, greenhouse gas emissions, and its effects on climate change, right? Coal is definitely one of the dirtiest resources in that regard, but also sort of locally, the environment can be substantially affected from extraction of the resources as well. For natural gas extraction, traditionally what we call conventional gas is extracted in a technique like this, where essentially you tap down directly into a reservoir that contains a large amount of the resource that you're looking for. And so you have these pockets that of natural gas that you're essentially tapping into and extracting via this mining procedure. And so that was the standard for sort of many decades for natural gas extraction. And then in the sort of mid 2000s, this guy in Texas came up with this interesting technique known as fracking, and that opened up a sort of totally new world of resource extraction that had sort of really far-reaching implications in the energy sector due to essentially what it did for natural gas availability. And we'll be able to see some of those implications for energy use in just a second. So here, after this technique of hydraulic fracking was developed, it opened up all of these resources, particularly, well, all around the world, but in the US, it opened up a lot of resources for natural gas extraction that was previously unavailable. And it turned us from this sort of net importer of natural gas to a net exporter. And it also caused prices for natural gas to fall to a level where natural gas became as competitive and then now more competitive than coal resources. And so this procedure, essentially what it does is it's doing this horizontal drilling procedure where you go across this shale area that has lots of these fissures. And so as you pump water through these areas, it displaces all of the gas, and a lot of it sort of dissolves into the water, and you can extract it back up. And so this process can be seen here. There are definitely some environmental implications of this as well. There was a lot of worry about leakage into local water tables. And in fact, there were some pretty interesting videos that you can see where people can actually light the water coming out of their sink on fire. This was happening in some areas in Pennsylvania. And so, yeah, there are lots of environmental implications of this. The other one is that you can see that this process actually uses a lot of water. and the water that ends up getting used in this process, they can't really do anything with it. So it kind of just, it's this highly toxic water that kind of sits in these stagnant pools. And I actually haven't sort of followed up in recent years. So I don't know if they figured out a way to kind of dispose of it. But last I was looking into this, a lot of those wastewater reserves kind of just sit around and they don't have anything to do with them. Okay. So from in economics, we can look at some of the costs and the prices of coals and natural gas. You can see on the left here, prices of coal over the last 2 decades compared to the prices of natural gas. And essentially, after discovery of a lot of those fracking resources, the prices of natural gas has fallen substantially and essentially led to outcompeting of coal and to a large shift in dominance of electricity production coming from natural gas rather than coal. Okay, maybe I'll take a quick moment here, see if anyone has any questions about this. All right, we'll continue moving on then. So processing of fuels on the sort of left-hand side, and I had sort of briefly talked about this last class, but essentially what happens is when we want to do combustion of coal, it's not like, you know, these large like charcoal briquettes that you would see like if you're doing like a barbecue or something, right? The most efficient way of doing combustion is to essentially grind up your coal into this fine powder, right? It increases surface area and allows for more consistent and faster combustion of your carbon material. So the coal that gets extracted from all of your mining facilities, that gets shipped on over to, oftentimes this is actually taking place directly at the power plant. So goes through some hoppers in order to filter out any non-coal materials, gets ground up essentially into finer and finer powder, and eventually will go feed into the combustion chamber at the power plants, which we'll look at in a bit. For natural gas, essentially what you want to do is just to filter out any of the impurities. You don't need to do, it's the type of processing, right, is obviously going to be very different from coal. And so you're going to be either getting natural gas from oil and gas wells, or specifically gas wells. They'll try to separate the materials, go through processing plant again to remove impurities. And that's important for the combustion process to allow for consistency in combustion outcomes, which means that your turbines, which take advantage of this combustion, can operate as efficiently as possible. Yeah, in some cases, if you have impurities, for a lot of the types of turbines that we have nowadays, it's not going to be good for the turbines to be operating at like non-ideal temperatures and pressures and that sort of thing. So you definitely want to remove as much of the impurities as possible. And so these will ultimately get sent downstream to end uses. So mainly we're thinking about use in electricity to essentially spin turbines, but it can be used for other end uses as well, where you can use it to, for example, do heating of your home. People use natural gas, right, to cook on gas stoves. So there are a sort of variety of end uses besides just electricity production, but most of it will be used for electricity. Okay, so process of combustion. So this basic chemistry review, this is your generic process for combusting any sort of hydrocarbon chain. And that's essentially what we're going to be doing with any fossil fuel, right? And so the number of carbons and the number of hydrogens depends on the specific type of fossil fuel. The chains are going to be smallest for gases, and then longer for larger number of carbons for liquids, and then even larger number for solids. And of course, this in itself doesn't contain a lot of those impurities that we were seeing before, where you have nitrogen and sulfur and that sort of thing. But in a complete combustion equation, you're going to be combining with oxygen, right, to create CO2, water, and a whole bunch of heat. And that's what you're going to be taking advantage of, is the heat. So for natural gas, this is pretty straightforward. Our carbon is CH4, and that's going to produce 1 molecule of CO2 and water. However, the presence of impurities, which you can never like totally get rid of, or it's not economically feasible to get rid of everything. And because of this, you're going to have some things like nitrogen oxides, carbon monoxide, carbon dioxide, and all of these. And actually, I should also mention that part of it is that you're not feeding pure streams of O2 in the air, right? You also have things like nitrogen gas, which can lead to things like incomplete combustion, leading to NOx byproducts. And so yesterday, or sorry, on Tuesday, we had talked about compounds that were pollutants in the sense of greenhouse gases, right, leading to global warming. And so those would be things like carbon dioxide and methane. And then you also have compounds that are local air pollutants, which lead to health problems for people who might be breathing these compounds or byproducts of the compound once they sort of react in the atmosphere. And so these include things like NOx, carbon monoxide, sulfur dioxide, volatile organic compounds, and particulate matter. So those are bad local air pollutants. So coal combustion is like the total opposite of natural gas combustion. It's very complex, right? So, you know, we have these giant carbon molecules that also have lots of impurities, and a lot of those impurities are in the solids themselves. So they're not really feasible to remove, and therefore you get all sorts of crazy byproducts in addition to everything that you would see up here. Coal combustion has like fly ash, flue gas, bottom ash, boiler slag, all of these things. They'll also have a significantly higher amount of sulfur dioxide because of it's common to have a lot of sulfur in your coal molecules. Also can contain some metal things like mercury, arsenic, pretty bad stuff. There are actually a lot of regulations these days that have helped substantially in ensuring that a lot of this stuff gets captured at the power plant after its combustion. That's actually one of the reasons why you have these really tall smokestacks that contain a lot of things that can help filter out some of these materials, but it's never going to be perfect. And a lot of, particularly the gaseous byproducts are hard to pull out. Okay, so let's talk about heat engine cycles. And so this is essentially how we take advantage of the combustion, is to take that heat that's being generated from essentially blowing up that coal or that natural gas and extracting some work out of it. And so the way that we do this is with what's known as a thermodynamic cycle. And the sort of really important part of a thermodynamic cycle is that you can do it sort of over and over again. So you have some kind of initial state of your system. It goes through a bunch of stuff and it has to return back to its initial state. And then as it goes through the cycle, it can do some work, but due to the law of thermodynamics, you are always going to lose some energy to heat. And so we'll see some sort of really basic examples of this. And this isn't meant to be something that you need to sort of know in great detail, right? So this isn't like an in-depth engineering class, but hopefully this will give us some sense for you guys to understand how the energy is being extracted. So we'll go through a couple of these as we look at the technologies that are extracting energy directly. Okay, so the relevant cycles, the Carnot cycle, Rankine, we'll talk about Otto cycle later, and then the Brayton cycle. And so Rankine and Brayton cycle, or sort of, these are cycles that we see being used today in existing turbines. I mean, they're slightly more specific and complex than the sort of simplified Rankine and Brayton cycle right now, but for the most part, it's going to capture pretty well how each of these power plants technologies are capturing the heat from combustion. Okay, so the first thing that we'll talk about is the Carnot cycle. So this is what we would consider like a theoretical maximum in terms of the most that you could possibly get out of a thermodynamic cycle. This is like a theoretical thermodynamic cycle. You can't actually do something like this perfectly, because you're going to have losses in each of these steps that are sort of impossible to avoid. But the main idea is like you have some kind of hot reservoir here, right? And so this might be essentially capturing, this reservoir is basically where you're doing your combustion and increasing the temperature. And what this does is you have sort of a perfect isothermal expansion. And so as you have heat energy going in here, so that's going to move the piston up. You have adiabatic expansion here, and then it returns back to the initial cycle as you have heat leaving this chamber into your cold reservoir. And so this this is the basic, a basic way where you're essentially doing heat transfer to produce work. So again, this type of cycle isn't something that you'd be able to achieve in reality, but it's essentially giving us some sense of how heat can be used to do work. Okay. Oh, actually, I see. Did someone have a question?
I have a question. Can
See
you go
someone's
back to
hand
the,
raised. Maybe that was from a long time ago.
I have a question. Can you go back to the previous slide?
It's my, oh, sorry. Apparently my headphones connected to another device, so I haven't been hearing anything anyone's been saying for for a little while. So sorry about that. Can you repeat your question? It's my computer still. Yeah. Okay. Can you? Whoever was asking a question, can you repeat it?
I put it in the chat.
Oh, okay. Yes.
What does,
adiabatic.
Mhm.
Let me go back here. Okay, so adiabatic. So this is where heat heat doesn't enter or leave the system. That you're looking at. So so this is kind of where it's like a really idealized system, right? So in this second stage here, your piston is moving up, but it's doing that without any sort of temperature change. So you're allowing this piston to move without heat leaving the system, which is physically impossible. But yeah, if you could do it, it would. This is essentially what would be happening. That's why you don't have this sort of queue happening in steps 2 and 4. Okay. Any other questions, or any questions that I missed from before? All right. So let's talk about how we go from, so actually, if I go back one slide, so this, okay, I can see that I am turning heat energy via this thermodynamic cycle into mechanical energy, right? And so how do we go from mechanical energy into electricity, right? Which is kind of the end use for a lot of the energy that we use. And the answer is through a generator. And so essentially how this works is you have, basically if you the way that you can generate a magnetic field, right, is to be spinning this loop through a magnet. And so this is a way that we convert mechanical energy into electrical power. And so almost all the electricity that is produced, so with the exception of solar energy, wind, nuclear, coal, natural gas, all produce electricity essentially by spinning spinning something through this a generator. And when you spin a sort of copper wire like this in a magnetic field, it's going to induce an electric current to be produced in that loop. And actually, you can do it in the reverse as well, which is actually exactly what a motor is. So a generator and a motor are the same thing, but they're going in sort of opposite directions. So you can spin the loop to produce a magnetic field, or you can spin the loop within the magnetic field to produce the current. So this is essentially how all electricity is going to be produced. And we're going to look at different techniques that we can combust our fossil fuels in order to achieve this outcome that we ultimately want. Okay, and so we do this via turbines to extract energy. And this is a way that you extract energy from fluid flow. And again, so almost all electricity on our planet is produced from these kind of turbines. So you can have steam turbines, gas turbines, water turbines, wind turbines. And so we'll think about steam and gas turbines today. This is kind of a simple diagram of how these turbines take advantage of this fluid movement to actually rotate. You don't need to know too much detail about this, but impulse and reaction turbines are sort of common forms of turbines that are used today. So you may have seen, oh, okay, so I see a
Professor, do you
question.
think we could go back really quick?
Yeah. So, okay, sounds like
Thank you so much.
some people have some questions. Okay, so fluid flow is synonymous with continuous, as in not intermittent. Yeah, so that's one way you can think of it. Although I think, strictly speaking, fluid flow is more about it's also about the kind of material that's flowing through here. And so you typically want things to act like a fluid. Yeah, so sending like gaseous streams or liquid streams through this is because of the mechanics of how it will sort of bounce off of the rotors within the turbine. That's kind of what you're looking for. Okay, and then there was another question.
I just have a question. So in general, when we're talking about turbines and generators, as a part of this course, should we be deep diving into the physics part of it, or should we just have an overall like understanding of how the things work? Like in case of a generator, should we know what the function of each and every part is, and how the electricity moves when magnetic flux is induced, and then how it moves in different directions, how alternate current is generated? Do we have to dive into all of those things, or just have a overall view?
Yeah. So this course is definitely going to be like at a higher level than that. So we're not going to be getting into like power flow and that sort of thing, and we're not really going to be getting into doing like physics and the sort of engineering equations that kind of dictate how a lot of these things work. This is definitely more to make sure folks have a sort of basic qualitative understanding of how these mechanisms work. So yeah, we won't really be getting too much into any of the like math and engineering behind this.
Got it. Thank you.
Yeah. Okay. So this is a picture of sort of a modern steam turbine. And so essentially what's happening here is that you have lots of stages of turbines. And so the way that I kind of like to think about this is that, or this, the way I kind of qualitatively describe this is, okay, if you have like one of those propeller fans in front of you and you blow into it and you cause that the blades of that fan to rotate, right? And you put your hand behind it, you'll still feel some of your the wind that you're blowing behind the fan. So there continues to be like potentially energy behind that first fan that you're blowing that you could be capturing. And so if you line up a whole bunch of them, you can imagine what would be happening is that the fans behind each one would be capturing a little bit of the energy that's going past the first one. And so essentially what that's what's happened. That's exactly what's happening in this turbine is it wants to be able to capture as much of that kinetic energy as possible. And so at the end of it, it's going to be sort of at a stage where you're not really going to be able to capture any more energy. And so these things are sort of really carefully designed to extract as much of the energy coming out or coming into that turbine as possible. And that's why you have so many sort of stages of these turbine blades. All right. So a steam cycle works in this sort of diagram. So this is a Rankine cycle. The sort of maximum theoretical energy that you get out of it is about 60%. In reality, the sort of most energy that you could get out of a sort of modern day coal plant, which operates in a steam cycle, is about 40%. And so that's really sort of at the absolute maximum. And so what essentially happens here is you have some water. It gets sent through a boiler. And so the energy of the system is being injected at this boiler step where you are combusting your fossil fuel to heat up the water. And that water then gets boiled off into steam at higher pressures and sent through this turbine. And that turbine is going to spin, and that mechanical energy of the spinning of the turbine is what's going to be powering your generator to produce electricity. And the water comes out of this turbine in sort of a lower energy form, right? The temperature and pressures are going to be lower. It gets condensed back into water and then goes through into a pump to move back through the boiler. Okay, and so this is a diagram of what you would kind of find inside of a coal plant, right? So we take that coal, we send it through the mill, right, to get it into sort of finer powder and send it into this furnace where it's combusted. Oh, sorry, I see a question. 0.85 is efficiency of the turbine. Yeah, okay, this number here, that's right, 0.87. And then what you'll notice here is that there's like a separate loop here of water that will cool the water coming out of the turbine that you can no longer extract any work out of. But the water going through the turbine itself is in a closed loop. And that ensures that this turbine can operate in the sort of maximal efficiency, because the water here is really purified. It doesn't have impurities that will damage the turbine or make it operate less efficiently. And the water that's cooling it, that's actually the stuff that you see evaporating out of the cooling tower. Okay, and so specifically for coal plants, you're going to see if you were to like walk up to a coal plant from the outside, you'll typically see two sets of towers. One is the cooling tower, which only emits water vapor, and so this is oftentimes coming from like a local water source. That's why a lot of these things are located like directly on rivers. It's just like river water being evaporated, and so that's fairly benign. And these towers are typically going to be much closer to the ground because the water vapor is not like toxic or anything. And then you oftentimes will see a very tall sort of chimney stack, and that stuff you don't want to be breathing. Those are the byproducts of the combustion. And the stack again is really long because it contains a lot of like filtering mechanisms to collect as much impurities as possible. But what's coming out of that chimney stack is definitely not just carbon dioxide. Oh, okay, I see a comment here. So there's also heat exchangers, so the steam and the cooling water do not mix. Yeah, exactly. So that's this 6 part here. So the heat exchangers here again. So like this loop is a closed loop. So none of the water that's going through the turbine is going to be mixed with any of the cooling water, which is important, right? Because you don't want to send impurities through the turbine. Okay, so that is for a steam plant, which uses water to do this stuff. And then you have a gas turbine, which is similar in principle, but instead of sending steam through the turbine, this actually uses combustion of natural gas to power it. Okay, so there are 3 components here. So you have an upstream gas compressor. And so this front part here is a compressor that basically sucks in air and pressurizes it so that you can have an airstream sort of going through. And the whole turbine is sort of operating on the same shaft. In the middle is where you're going to have your combustion taking place. And so that is essentially what's going to be producing the work that's going to be essentially spinning this turbine. And so after the combustion at higher pressures, it's going to extract the work through this series of turbines here and push out this hot exhaust gas. So question from Francisco, the combustion powers the air suction. That's exactly right. That's how you get the sort of upstream stuff to spin. So another comment, it's like a jet engine, very loud. So that's exactly right. It literally is a jet engine. So the gas turbines that you see on like a commercial jet, that is exactly what this is. And you could very simply tear one of those off of an airplane, stick it into a power plant, and do exactly what you want it, exactly what this is doing in a power plant. You probably couldn't do it in reverse because they're not like ideally designed to, like, you couldn't go into a power plant and take the turbine and stick it onto an airplane. They're not designed in exactly the same way. They don't have the scaffolding, but in principle, right, the gas turbines are essentially the same design, same thing. Okay, so this gas turbine is a Brayton cycle with an efficiency in practice a little bit higher than in the Rankine cycle. This is closer to 50%. And so again, you have your air coming in along with the fuel combusting inside, and then providing the energy to spin the turbine, and you get work out. And then you have these really hot exhaust gases out of the other end. And yeah, so the natural gas does get injected directly into the combustion chamber. That's right. Okay. And so one of the interesting features of this is that that you get these hot exhaust gases that are still very, very hot out of this turbine. And so what natural gas plants will do to take advantage of this is actually combine the Brayton and Rankine cycles. And this actually allows for the efficiency to be substantially higher. So instead of this like mid 40% efficiency, you're getting up to 65% efficient by combining both of these together. And this is what makes natural gas plants to be substantially more efficient than coal plants in terms of extracting the primary energy. So so if we look at the gas turbine, it's just exactly the same as before, except now you have this hot exhaust gas, which you can use to heat up water, right? So that you can think of this as equivalent to kind of the boiler in the coal plant. And so by heating up the water, you can send the steam generated through a second steam turbine to capture energy in that original Rankine cycle. And so you have in a natural gas power plant, oftentimes in a combined cycle plant, you're going to have both the gas turbine as well as the steam turbine. And this allows for much higher sort of efficiencies. One of the things that I'll sort of note as an aside is that the gas turbine can operate and ramp up to sort of produce electricity very quickly, right? You can essentially start this the turbine spinning and combust your natural gas and extract energy to power your generator very, very quickly. Whereas within a steam turbine, you have to spend some time to heat up and boil the water, get it up to its ideal sort of operating state. And so you can imagine that in like coal plants and even in some combined cycle plants, that boiling all that water, a substantial amount of water, can take a little bit of time to do. And so the ability of like a combined cycle plant or a coal plant to respond to electricity needs can be slower. And that has some implications for how these plants get used, how they're scheduled to be used, and how fast they can respond to sudden needs in like electricity demand. Okay, so we're on the hour right now. I have 11:03, so why don't we take a quick 5-minute break? Yeah, again, I'll stick around in case people have any questions or anything like that. But we'll start again at 11:08. Okay. Let's get back into it. So this picture is what you might find at a typical combined cycle power plant. And importantly, you can see that this particular one contains both a gas turbine and a steam turbine. That's what makes it combined cycle. So you're doing both the Brayton and Rankine thermodynamic cycles here. Someone actually mentioned before, very loud. Yeah, I've visited one of these before, and the turbines are incredibly loud. They make you wear all sorts of like earmuffs for noise protection. Okay. This is a map of power generation facilities. So these are basically all the power plants throughout the United States or the continental United States. The size of the dots correspond to the capacity, right? Again, so the capacity refers to the amount of power that the peak power that a power plant could produce in a given amount of time. So essentially the larger the dot is, the more power they can produce. And the color refers to the fuel type of the power plant. So this map itself is probably a couple of years old at this point, so things probably look a little bit different, but for the most part, a lot of the patterns are going to be pretty consistent. So you'll notice that in California, for example, there's a lot more pink, which is solar power, right? You see that more sort of prevalent in the Southwest and sort of on the East Coast, but not so much sort of utility scale power in the Midwest and in the South. In the Pacific Northwest, there is sort of the highest density of hydropower, which you see in the green. There are some orange dots that you see throughout the country, and these are nuclear plants, and they're all quite big. In California, you'll notice there's still sort of one plant here. This is the Diablo nuclear power plant, which is located near San Luis Obispo. It's the last nuclear power plant in California. For better or worse, we'll get into some of the sort of nuances and politics of nuclear power in our next class. But this power plant is scheduled to get retired in 2025, so pretty soon. We were talking a lot about coal and natural gas plants today, and what you'll notice on the West Coast is that you have a lot fewer coal plants. In fact, there are no real operating coal plants in California. There's technically one, but it's kind of like a legacy thing. It's not really for any serious power production. But so basically, you can think of California as being free of any coal power. We do have, however, a substantial amount of natural gas, which is the purple. And in fact, natural gas has really kind of exploded over the last 2 decades. Again, thanks to this thing that happened with fracking. And so you can see a sort of big plethora of these purple plants happening all throughout the country, and you'll definitely still see a lot more sort of coal more situated in the eastern half of the country, and so those are the blue dots. there's a lot of gray in the Midwest. That's wind. That's where a lot of the highest and best wind resources are available. And so that's why you see them sort of cluster around here. It kind of makes sense for that to, for these to be the kind of location for that. Okay.
I have a question.
Yeah.
So the nuclear power plant in the Diablo,
Mhm.
that's closing down in 2025. Is that closing down because it's reaching its operational end of life, or just like political reason or stuff like that?
Yeah, definitely. Well, it's a little bit of both. So nuclear power plants are usually a lot of the ones that were constructed back in the 70s, 80s. The sort of lifetime of a lot of these power plants is around 40 years. And so as nuclear power plants sort of reach that retirement age, there are certain decisions that are made about whether to retrograde, upgrade it, and update that power plant, which has happened in several cases, or to simply kind of shut it down. And some of the political pressures and sort of public sentiment have led to decisions to not do things like retrofits and upgrade the plants, and instead to go ahead and shut them down. So it's a combination of both. This definitely isn't like my particular focus and area of expertise. I'm not aware of any plants that get shut down early because of political pressures, but it can lead to the decision making to not pursue like upgrades or construction of new plants.
Thank you.
Mm-hmm. And in fact, so we can see in this neat little chart here on the left hand side, this is basically a graph that shows when new capacity was installed. So you can see, a lot of this before are these smaller sort of hydro power plants, and then starting in the 50s and 60s, we started to install a lot more power production coming from fossil fuel generation, so both coal and natural gas, right? The red is the nuclear, and so you can see in the 70s and in the 80s is the sort of big period of time in which there was a substantial installation and construction of nuclear power plants, and that has since kind of faded away. And so if we think about the lifetime in terms of like 40 years, well then sort of starting in the sort of 2010, 2020 timeframe is when you're going to start to see these decisions being made about retiring the nuclear plants or whether to sort of keep them operational. And then in the sort of more modern era over the last 2 decades, you can see this thing that I was talking about, right? A lot of this influenced by the fracking shale resources that we're getting to get a much higher availability of natural gas in as a domestic resource, leading to this huge construction of natural gas plants. And then again, more recently, right, you're getting a substantial amount of construction of renewables. And so, speaking from, someone concerned about climate change and sustainability issues, I had shown last class a chart about the production of electricity and energy used from renewables still being kind of relatively small, right? But you're talking about resources that are growing against a capacity that's been installed over almost an entire century in the past, right? And so I think it's still promising that the trend for new installations is really dominated by renewables. And so it's pushing us in the right direction, and whether that's good enough or fast enough is kind of a separate question. And on the chart on the right, yeah, so this gives some perspective about generation by your different fuel types. So up into the 2000s, right, we can see the clear trend is that coal is the dominant fuel type. But again, once fracking sort of happened, you can see natural gas starts to outpace coal, and in fact today is producing more electricity from natural gas than we are from coal. And that's actually quite a good thing in terms of emissions reduction. So for the same amount of electricity production, natural gas combustion is going to get you about half the emissions that you would be getting from coal combustion for the same amount of electricity. So it's not like natural gas definitely isn't like a silver bullet or anything, but in terms of sort of raw total emissions reduction, it's actually one of the biggest contributors for emissions decrease in the electricity sector, is this shift from coal to natural gas. Okay, so basic layout of our electricity grid. So we talked about electricity getting produced by your power plants and eventually getting sort of transmitted all the way down to its end use. And so the way this works is it has to go through transformers, step up in voltage, goes over these really large scale transmission lines. And so these are like the big metal towers that you might see if you're driving down the freeway, goes to these substations to drop down in voltage. And then this goes into distribution substations. So these are more like the local sort of wooden electricity poles that you see around town. And so this eventually gets brought into your end use directly. And again, this is not like a power systems class or anything. So we're not going to be doing power flow or trying to understand all the sort of details in the mathematics behind how like electricity operates and phases of electricity or anything like that. Just a high level sort of understanding of how electricity gets from point A to point B. And part of the point here is that in your transmission and distribution systems, and as you go through your transformers, there's always a little bit of energy loss happening. It depends on the distance that you transmit the electricity, but roughly speaking, this transmission system and this distribution system are going to be losses on the order of a couple percent. So think anywhere between 1 to 5% in your transmission system, and then another sort of 1 to 5% in your distribution system, where 5% would be definitely pretty high. I can't speak to like the actual average, but I think it's going to be a lot closer to around like 2% losses. And that is in contrast to, remember, in your generation, your power plant, you're talking about losses from your primary fuel source on the order of, 30 to 60%, or sorry, 40 to 60%, depending on the efficiency of your thermodynamic cycle. And if you remember from last class, we saw a little bit of that. That's where most of your losses are going to be happening. Okay, so last couple slides thinking about some of the environmental impacts. So thinking about greenhouse gas emissions. So I just kind of want to step back at a really high level, thinking about the carbon cycle and how carbon fluxes happen in the sort of environments and in the atmosphere. This is ultimately why, at least I'm sort of interested in this, right? Thinking about climate change issues. So in the sort of natural side of things, you have set of exchanges of carbon, right? This is mainly through carbon dioxide, where respiration of living organisms will emit CO2. So that's the arrow going out into the atmosphere, and then photosynthesis will take in CO2. And actually in nature, those are roughly in equilibria, where the amounts are relatively similar. You have something similar happening for ocean exchange as well. And so again, balanced out. From anthropogenic side of things, we have emissions of CO2 sort of in excess. And so these fossil fuels, right, are just emitting CO2 after the combustion, as a combustion byproduct into your atmosphere. And this particular arrow, right, is not being balanced out by anything. And so roughly in terms of magnitude, the quantity of that these days is roughly similar to the magnitude of all sort of natural side of carbon dioxide or carbon getting emitted into the atmosphere. So we're approximately doubling the carbon flux into the atmosphere with only half of it getting sort of retaken. And so that's what's leading to a buildup of carbon dioxide concentrations in the atmosphere and ultimately leading to global warming. Okay, so last slide here, again, sort of talking about this this discovery of fracking, right? And so we can see that coal energy consumption has been replaced at nearly a sort of 1-to-1 ratio with natural gas over the last decade and a half or so. You can see coal sort of falling substantially while natural gas is growing at the same, almost the same rate that coal is falling. And what this means in terms of emissions, right, is that as I was saying before, combustion of natural gas compared to coal, it has about half the level of emissions. So in a 1-to-1 replacement, coal emissions has decreased by about 700 million tons, right? So this slope falls about twice as fast, while natural gas emissions has increased by about 300 million tons annually. So again, natural gas is a fossil fuel. Combustion of it does still lead to emissions of greenhouse gases. But in terms of sheer volumes of reduction, the replacement of coal by natural gas is like far and away the biggest reduction that we've seen in the energy sector for emissions, more so than I would say most sort of policies that are kind of getting our emissions to decrease have done. So Okay, so that's actually, I think, all I have for today. And so we're going to end a little bit early here. Again, I will get back to everyone about what we're going to do definitively for next week's lecture as soon as possible. I'm going to figure out some logistical things, then I'll send a message on Canvas. So in the meantime, yeah, don't worry about that rescheduling that I had done. So there will be no extra lecture tonight and tomorrow. It's just going to take place at the planned time and the set schedule next week. Good. So I will see everyone next week, either on Zoom or in person, depending on what we end up doing. And yeah, I'll stick around a couple minutes in case anyone has any questions. Otherwise, have a nice rest of the week.